Okay, let's talk about something that honestly feels like a math cheat code. We're going to find a shortcut for handling complex numbers, a way that's going to make the old method feel, well, totally obsolete. Let's get right into it. So, have you ever been there, you're trying to multiply two complex numbers, and you're just lost in the weeds of all the algebra? I mean, it gets so messy, right? And it just takes one tiny little slip-up to throw the entire answer off. It's frustrating.
Yeah, I'm talking about the old FOIL method. First, outer, inner, last. We all learned it. And look, it works, sure, but man, is it a grind. You've got to multiply every single term, then you have to remember that I squared is -1, then you got to combine all your like terms. It's a lot. But what if I told you there's a much, much better way?
Well, guess what? There is. And this shortcut we're about to look at, it isn't just faster. What's really cool is that it gives you a much deeper, kind of visual feel for what's actually going on when you multiply or divide these numbers.
So here's the secret sauce. The key is to completely change how we look at complex numbers. We need to stop thinking about them in that standard a plus bi rectangular form. The moment we switch our perspective over to polar form, all that messy algebra, it melts away into really clean, super simple arithmetic.
All right, let's get to the good stuff. This whole power move, this whole trick, it really just boils down to two incredibly simple, almost beautiful rules. But before I just throw them at you, there's one little bit of notation we got to clear up first, just to make sure the formulas are crystal clear. Okay, so you're going to see this term cis, C-I-S. And no, that's not a typo. It's actually a super clever shorthand. It just stands for cosine plus I sine. So when you see something like r cis theta, all that means is r times cosine theta plus I sine theta. It's just a cleaner, quicker way to write the polar form, and it's going to make our rules look way less intimidating.
And here they are, the two rules that change everything. For multiplication, you just multiply the lengths, the r values, and you add the angles. For division, you divide the lengths and you subtract the angles. I mean, just look at that. It's so clean, so symmetrical.
Goodbye, FOIL! So, for multiplication, let's just burn this into our brains. The mantra is multiply moduli, add arguments. And remember, moduli is just the fancy word for the lengths or the r values. Arguments are just the angles or theta. So you just multiply the lengths, add the angles. Simple as that.
And for division, you guessed it, it's just as nice. Divide moduli, subtract arguments. Now the one little thing you got to be careful about here is the order. It's always the first angle minus the second one. The numerator's angle minus the denominator's. Don't mix them up. What's so cool about this is that it actually shows you what's happening geometrically. When you multiply two complex numbers, all you're really doing is scaling the length of one by the other and then rotating it by the second number's angle. And division is the same idea, just in reverse. You scale the length and rotate it backward. It's just scaling and rotating. That's all it is.
All right, enough with the theory. Theory is great and all, but let's actually see how this works with some numbers. Let's run through a couple of examples so you can see for yourself just how powerful and easy this is. Okay, example 1. Let's multiply 3 cis of pi over 4 and 2 cis of pi over 6. So what's the rule? Multiply moduli, add arguments. So we multiply the moduli, 3 times 2, that's 6. Then we add the arguments, pi over 4 plus pi over 6. Find a common denominator, and you get 5 pi over 12. And that's it. We're done. The final answer is 6 cis of 5 pi over 12. Seriously, how easy was that compared to FOIL? All right, let's try division. We've got 8 cis of 2 pi over 3 divided by 4 cis of pi over 6. Rule says divide moduli, subtract arguments. So 8 divided by 4 is 2. Easy. Now for the angles. 2 pi over 3 minus pi over 6, that gives us pi over 2. So the answer is 2 cis of pi over 2. And here's the cool part. What is cis of pi over 2? Well, cosine of pi over 2 is 0, and sine of pi over 2 is 1. So that whole thing just simplifies down to 2i. So satisfying. Okay, but what happens if they give you a problem that starts in the old rectangular form? Like 1 plus I times radical 3 plus I. No worries at all. Step 1 is just to convert both of them into polar form. 1 plus I becomes root 2 cis pi over 4, and radical 3 plus I becomes 2 cis pi over 6. And hey, from there, we're on home turf. We just use our rule. Multiply the moduli, root 2 times 2 is 2 root 2, and add the angles. Pi over 4 plus pi over 6 is 5 pi over 12. Done. The solution is 2 root 2 cis 5 pi over 12. We just completely dodged that whole FOIL nightmare.
Okay, so the rules are awesome because they're so simple. But that simplicity can sometimes be a trap. It's really easy to make a small mistake if you're going too fast. So let's talk about a few of the most common pitfalls so you can watch out for them.
First off, the biggest one I see, people accidentally multiply the angles instead of adding them. Just keep repeating the mantra in your head. Multiply moduli, add arguments. Another big one is for division, getting the subtraction backward. Remember, it's always the angle on top minus the angle on the bottom. And one last thing, if your final angle is something huge, like bigger than 2 pi, it's just good form to simplify it down. Bring it back to a value between 0 and 2 pi.
So I know what you might be thinking. Okay, this is a cool trick for my pre-calc class, but when am I ever going to use this in real life? Well, the answer might actually be sitting on your head right now.
I'm talking about your noise-canceling headphones. Yeah, seriously. That amazing technology that creates your own little bubble of silence on a loud flight or a busy commute, it is built on the exact math we've been talking about.
So check this out. It's kind of mind-blowing. Engineers can actually represent sound waves as complex numbers. They call them phasors. Your headphones have a tiny microphone that listens to the noise around you. Then the magic happens. The electronics inside have to instantly create an anti-noise sound wave, one that's perfectly out of phase to cancel out the incoming noise. And how do they do that? They rotate the phase of the sound wave.
And how do you think they rotate the phase of that wave? You got it. They do it by multiplying it by another complex number using the exact polar multiplication formula we just went over. They are literally adding an angle to the sound wave's phase to create that perfect anti-noise signal. Isn't that wild? It's one of the coolest real-world applications of this seemingly abstract math. So, we've cracked the code for multiplication and division, but that kind of opens up a new door, right? I mean, if raising something to a power is just repeated multiplication, what happens when you raise a complex number to, say, the 10th power? Well, that is where this method becomes an absolute superpower. It's a concept called de Moivre's theorem, but that's a story for another time. I really hope this helps make sense of this topic. Thanks for hanging out with me.